Hello, all of my teachers. First of all, I would like to say thank you for give us such wonderful opportunity to present our project. We are from Techno College of Engineering Agartala with specialized branch Electronics and Communication Engineering. Today we are here to represent our project that name Supply Noise Aware Application Specific Integrated Circuit Design. We are doing this project under the guidance of Assistant Professor Ms. Ghumur Bhumik ma'am and External Supervisor Dr. Dabojit Dev sir. Myself, Udayan Chakraborty, and my project partners are Shubhra Majumdar and Dabru Pathak. These are some outlines of our project. Objective of project, introduction, literature, results and discussion, future scope, conclusion, and references. In most of the cases, when working with less nanometer technology, it is found logical failure at the output. This is due to power supply noise. So, the main objective of our project is to reduce that noise. One question is arises how this noise is generated in ICs. This is due to the presence of package. Package is nothing but the semiconductor material which is used as an input or output pins in IC. It is the last step of IC fabrication. Effect of many electronics component can be seen in this package, where the effect of inductance is found as much as other components. That's why we use inductance as a package in our design circuit. As we know from the behavior of inductance, that current lagging behind the voltage. And when the IC comes from sleeping mode, sudden current jump occurs due to this package inductance. This ramp is known as noise, as the noise is flowing separately through the all over the network in our ICs causes we found some abnormalities at the output. The figure S see the package available in ICs. That cause in figure B we can see it affect output functionality with glitches available at output wave. During our project work, we have followed some literature. Two of these are described here. First one is power supply noise aware physical design with decoupling capacitance allocation on signal on chip. In this literature, the researchers mainly focused work on the allocation of decoupling capacitor so as to reduce the power supply noise. In this equation, they are going to explain how they estimate the value of capacitance. The second one is power supply noise rejection improvement method in modern VLSI design. Here, the researcher have used MOS and MOM circuit, where MOS stands for metal oxide semiconductor and MOM stands for metal oxide metal. They use this MOS and MOM instead of using capacitor to reduce the noise. Shubhra will continue from resultant discussion.
Now I will start to discuss the result and discussion of our project. In our project, we were working of CMOS D flip-flop for reducing the power supply noise. It is the block diagram of CMOS D flip-flop. It is the transistor level diagram of CMOS D flip-flop. In here, total 18 number of transistors used. In here, we have examined the power supply noise at different operating frequency with 1 microhenry and 24 picohenry package inductance in AT&T CMOS D flip-flop. As per result, we see out of all operating frequency, only 1 microhenry package at 0.03 GHz operating frequency has passed. Here we shown the waveform of 24 picohenry package inductance at 0.06 GHz operating frequency for both technology in AT&T CMOS D flip-flop. Here the output indicating success for both technology. Here we shown the waveform of 1 microhenry package inductance at 0.03 operating frequency for both technologies in 18T CMOS D flip-flop. Here the output indicate logical failure in 45 nanometer technology. The output indicate logical failure at less nanometer technology. If technology is less, the current is passing in the circuit very high. If current is high, then the noise which is occurred due to sudden current ramp, it also goes to high. Next, Deborah will continue.
Now I am going to discuss about the rest of the result part in our project. Here we examine the power supply noise for different packages at same operating frequency, which is 0.03 GHz for 500 nanometer and 45 nanometer technology in 18T CMOS D flip-flop. After examining all the parameters, we see that out of all the parameters, only 1 millihenry at 0.03 GHz operating frequency for both technologies are shown failure, where other parameters are shown success. This is the waveform of 1 millihenry package at 0.03 GHz operating frequency. In here, for both technology, the output does not follow the logic of DE, that is, it indicates the logical failure due to large package, because if package is large, the current flow in the circuit is very high. As a result, power supply noise is occur. Again, we design CMOS D flip-flop, but here we use only 10 transistors in this diagram. After design 10T CMOS D flip-flop, we have again examined the power supply noise for different operating frequency with 1 microhenry and 24 picohenry package. As a result, we see that all the outputs are success. The output indicating success because here we use less number of transistors. In this waveform, we have compared 18T CMOS D flip-flop and 10T CMOS D flip-flop for 1 microhenry parameters at 0.03 GHz operating frequency in 45 nanometer technology. The output of 18T CMOS D flip-flop are shown failure due to using more transistor. But in case of 10T CMOS D flip-flop, the output indicating logically success due to using less number of transistor. Now Shubhra will continue.
Then we have examined the power supply noise of different package inductance at same operating frequency for both technologies in 10T CMOS D flip-flop. As per result, we see the output of all different package inductance at same frequency for both technologies are indicating success due to using less number of transistor. Because when we reducing the number of transistor as well as the current is also reduced, if current is reduced as well as the supply power noise will be reduced. Here we shown the waveform of 1 millihenry package inductance at 0.03 GHz operating frequency for 500 nanometer technology. And here we also shown the waveform which is compare 18T CMOS D flip-flop with 10T CMOS D flip-flop. As per result, we see the output of 10T CMOS D flip-flop indicates success due to using less number of transistor. But in the case of 18T CMOS D flip-flop, the output indicating logical failure due to using more number of transistors. Here we shown the waveform of 1 millihenry package inductance at 0.03 GHz operating frequency for 48 nanometer technology. And here we also shown the waveform which is compare 18T CMOS D flip-flop with 10T CMOS D flip-flop. As per result, we see the output of 10T CMOS D flip-flop indicates success due to using less number of transistor. But in case of 18T CMOS D flip-flop, the output indicating logical failure due to using more number of transistor. After that, we have designed a CMOS combinational circuit. Here, the package inductance is added to VDD or voltage source. When the current passes through the package, the noises affect the output logic functionality. Here in the waveform, we shown the noise affecting output functionality area. Next, Udan will continue.
It is the proposed design of previous combinational circuit. Here we are use P-type MOSFET as a decoupling capacitor. When VDD is applied, the generated noise is passing through the pull-up network. The drain terminal of pull-up network is connected to the MOS capacitance, from where the supply noise is bypassed to the ground terminal, and most of the noise absorbed by this MOS capacitance. Let's see the output functionality of this proposed design. Here we see no noise is occur at the output. This same technique is used in D flip-flop 18T logic, where we use 18 numbers of transistors to design D flip-flop. For these 5 networks, we have 5 number of MOS capacitances. We again analyze the output at various operating frequency. Here, all the cases are found logical success. We also change the package inductance at various operating frequency to check the output VPP. Here one thing is that the VPP for 500 nanometer technology is much more higher than the 45 nanometer technology. But why? This is because by decreasing the channel length of the MOS capacitance, large current flow through the gate to bulb terminal. As the current flow high, then noise also high, because current is directly proportional to the supply noise of D flip-flop or any other electronic circuit. Let's check the output by comparing the previous one and the proposed design. We can observe that the output of proposed design is success. Now Devrupa will continue.
Then we examine the power supply noise for different parameter at same operating frequency, which is 0.03 GHz for both technologies in CMOS proposed D flip-flop circuit. As a result, we see that out of all the parameters, 1 millihenry at 0.03 GHz for both technologies are showing failure, where other parameters are shown success. Here we have compared 18T CMOS D flip-flop and 18T proposed D flip-flop for 1 millihenry at 0.03 GHz operating frequency for 45 nanometer technology. The output indicating failure due to large package inductance. But as compared to 18T D flip-flop, the output of proposed D flip-flop is little bit same as the output logic of D in. Then again, we compared 18T CMOS D flip-flop and 18T proposed D flip-flop for 1 millihenry at 0.03 GHz operating frequency for 500 nanometer technology. The output indicating failure due to large package inductance. But as compared to 18T D flip-flop, the output of proposed D flip-flop is little bit same as the output logic of DE. Now Shubhra will continue.
So here it is. There are some future scope of our project. First one is layout and post-layout supply noise analysis of IC circuit. Second is noise analysis of finite state machine and Intel benchmark circuit for design validation. And the last but not the least, hardware implementation of MOS level logic circuit and observation of noise deviation with simulation. It is the conclusion of our project. The first point is we understand the supply noise is a very real problem for optimizing VLSI circuit. Second is we have examined the supply noise level of D flip-flop for both technology, 500 nanometer and 48 nanometer technology. Number 3, at summer operating frequency, the supply noise of sequential is reduced due to less current drawn by package inductance. Now Udin will continue.
The analysis has been done considering different package inductance values for small channel devices. By reducing the number of transistors in a corresponding circuit, we can reduce the noise. Modify the design by using P-type MOSFET in pull-up networks The supply noise is reduced because the extra PMOS act as a decoupling capacitor. These are some references that we have followed during our project work. Thank you.